Hi there! Welcome to the second program in our 2023 Sawtooth Forum and Lecture Series, brought to you by the Sawtooth Interpretive and Historical Association. I'm Heath Bagley, a naturalist at the Redfish Visitor Center. I want to take a moment to acknowledge that here in the Sawtooth country, we are on the unceded and traditional lands of the Agadeka and Dukadeka bands of the Shoshone-Bannock tribes. We pay respect and honor to the tribes and all indigenous people who have continuously stewarded this land for generations. This program is free of charge thanks to our primary sponsors, the Redfish Lake Lodge and the McNichol family, in memory of Roland McNichol, who was an avid series attendee and a steward of the Sawtooths. We thank our sponsors for their continued support. As you may know, the association is a member-based nonprofit. Our mission is to protect and advance the natural and cultural history of Idaho's Sawtooth Salmon River country throughout preservation and education. Our operations are funded by donations, grants, memberships, and book and map sales at our bookstores located inside 9 ranger stations, as well as the Redfish Visitor Center and Gallery here in the Stanley Museum. We hope you will consider supporting our work by making a donation tonight in our Sawtooth Bowl, using your credit card in our handy dip jar, or by becoming a member. Would any current members of the CHA in attendance please raise your hands? Woo! Thank you for your support. If you have questions about being a member or anything else, come find one of people like me in blue shirts, and we'll be happy to help. Tonight we are excited to bring you Dr. Katie Potter, representing What Lies Beneath, How the Idaho Batholith Influenced the Yellowstone-Snake River Plain Supervolcanoes. Katie Potter was raised in southwest Colorado between the Colorado Plateau and the San Juan volcanic field. Her fascination with volcanoes began early, and she spent her scientific career exploring the links between crustal architecture, hotspot magmatism, and the eruptive characteristics of volcanoes in the Snake River Plain and Walvis Ridge. Katie received her BS at Fort Lewis College, her MS at Idaho State University, and her PhD at Utah State University. After forays in the mining and oil and gas industries, she's now an assistant professor of professional practice at Utah State University. Please give a warm welcome to Dr. Katie Potter.
All right, thank you for that warm introduction, Heath, and thank you all for having me today. I'm very excited to present this. It's a culmination of a few years of research, and most of it is unpublished, so you're kind of my guinea pigs. I'm going to share this with you, and you can tell me if you think it's bogus. But I'm thrilled to be here. It's so fun to give a geology talk in the rocks that you're going to be discussing. It's a rare treat. So it's really fun. Thank you for having me. It's also a lot cooler up here than it is in Logan, so that's another bonus. So in this presentation, I'm going to share with you how a tiny mineral links together the building of North America, so crustal architecture, as well as the creation of the Idaho Batholith, and the timing and eruptive characteristics of supervolcanoes along the Yellowstone-Snake River Plain hotspot track. And throughout this presentation, I'll be referring to figures and maps and graphs that are in the packets that I hope most of you have. And if you've leafed through the packet and you see some things that concern you, it looks like you're going to get tested on this at the end. Let me put those worries to rest. I'll be walking you through all of this stuff throughout the course of this presentation, and mostly this is just to help illustrate concepts that I'm going to be covering. This is my first time doing this presentation without a PowerPoint, so I'm going to rely a lot on hand gestures and my little script up here, and then there will be a lot of time for questions at the end. So if you want to scribble those on your packets, that's a good thing to do. Okay, so let's have our first geology lesson. On the first page of your packet, you'll see a picture of a rock. This isn't just any rock, this is actually a photograph of a rock found in the Idaho Batholith. And here in Stanley, we're basically surrounded by rocks, outcrops of the Idaho Batholith. So the major minerals that make up the Idaho Batholith are quartz, which is the light gray mineral in your packet. I'm thrilled that this isn't black and white, but I guess it wouldn't really matter because all these minerals are that shade. And in those white minerals that you can see in the photograph are sodium-rich plagioclase feldspar, which we call albite. The dark-colored minerals are hornblende and biotite mica. And collectively, these are all the primary minerals that make up the granodiorites and granites of the Idaho Batholith. And we know that the Idaho Batholith cooled slowly deep underground because we can see all of these minerals with our naked eye. We don't need a microscope to be able to pick these minerals out of the rock. And so that's one of the ways that we can name the rock granite or granodiorite. However, the link between the Idaho Batholith and supervolcano eruptions of Yellowstone and the Snake River Plain is found in a mineral that we can't see, a tiny but incredibly strong mineral called zircon that, thankfully for geoscientists like me, is very common in the Idaho Batholith and a lot of the crustal rocks around here, as well as those volcanic ash deposits that were erupted when those supervolcanoes popped off. Before I get too carried away sharing the virtues of zircons, I'd like you to hold up your palm, your mini hand, right or left, so that your palm is facing you, and look closely at your fingertips. Really zoom in. See if you can characterize your fingerprints. And now after you've done that, after you've familiarized yourself, ask your neighbor if you can take a look at their fingerprints. Very good. Alright, don't get too carried away. Hopefully you've all recognized that the ridges and whorls on your fingertips are unique to you. They're distinct to your hand. They're different from your neighbor's. And just like your fingerprints, no two zircons are the same. Or I should say, just like your and your neighbor's fingerprints, no zircons are the same. Zircons contain chemical information that provides clues to their origin and age. And importantly, although they're too tiny to see with the naked eye, they're extremely durable, so they don't break down due to heat and pressure. So in figure 2 of your packet, you can see a typical fingerprint next to a representation of a zircon. The zircon shows zonation. I'll let this truck pass. The zircon shows zonation, which are similar to growth rings, and those form as the zircon crystallizes in a magma reservoir. You can think of mineral zonation as being like tree rings, and that as a tree adds a new ring each year, zircons add new rings after each crystallization event in the magma. If we measure the age of a zircon, we can see that the youngest part of the zircon is on the outside, or the rim of the zircon, and the oldest part of the zircon is at the inside, or the core of the zircon. Each zone has a different age, and as we move progressively outward toward the rim, we see younger ages, and as we move progressively inward toward the core, we see older ages. Since these zircon rims kind of crystallize from different magmas, each zone can have a distinct chemical signature that also provides us information about what's happening in the magma chamber and what surrounding rocks might be melting to create that magma. So you might be wondering how zircons and supervolcanoes relate to the story of the Idaho Batholith. If so, you're in luck. You're in the right place. During this presentation, I'm going to show you how zircons can help you understand how rocks like the Idaho Batholith have contributed to the architecture of the continental crust in the northwest United States, how rocks like the Idaho Batholith have influenced supervolcano eruptions that took place over the last 17 million years. But first, let's establish ourselves geographically and geologically in space and time, starting around 100 million years ago, which is the late Cretaceous. There's some dinosaurs around, so not a great place to land if you're in a time machine. But during the late Cretaceous period, while much of the U.S. was submerged under a shallow sea, western Idaho sat in a region of high mountains and volcanoes, just east of the ancestral Pacific Ocean. You can see a map of what North America looked like during this time on page 2 of your packet, right in here. Idaho is outlined in black, and just for reference, Stanley is indicated by that orange dot. Actually, this area is really similar to the modern shoreline of Washington, Oregon, and Northern California. Just like the present-day Pacific Northwest, western Idaho sat along the margin of a subduction zone. And now it's time for our second geology lesson. I'd like all of you to take out your hands again. And what we're going to do is model plate tectonics. specifically subduction zones. And actually, before, put your hands back down, I'm not there yet. Subduction zones, along with other plate tectonic mechanisms like divergent boundaries where pieces of the crust spread apart and transform boundaries where they slide past one another, are the principal mechanisms by which Earth releases heat or accommodates convection in the mantle. This heat flow is coming from the core, and it's got to go somewhere. Basically what it does is cause these tectonic plates to move around. Alright, so to model subduction, I'd like you to hold up both of your hands and rest the fingertips of your right hand on top of the knuckles of your left hand. If you bend the fingers in your left hand slightly while pushing your hands together, you've modeled the subduction zone that existed about 100 million years ago off the coast of Idaho. In subduction zones, heavier oceanic crust sinks below more buoyant continental crust, and that's because they're made of different minerals. Oceanic crust is made of heavy minerals like olivine, pyroxene, and calcium-rich plagioclase feldspar, while continental crust is made of light minerals, less dense minerals, like quartz, plagioclase, sodium-rich plagioclase feldspar, potassium feldspar, and those micas. So subduction zones create new topographic features on the continents, like mountains, but they can also add to the continent. They can add land to the continent if that oceanic plate is carrying along with it islands. However, unlike the oceanic crust on top of the oceanic crust below these islands, those islands don't subduct. So the oceanic crust goes down, but the islands don't. And why do you think that is? Here's a quiz for you. Yeah.
Getting new layers on top?
New layers of what?
Magma?
Yeah, there's some magma involved. Think about density, though. Ingredients. What are these islands made of? Why are they floating? Why are they on top of the oceanic crust?
They're actually floating?
Well, not really floating, but they're not. They're not heavy. Yeah.
They're just less dense.
Yes.
Less dense minerals.
Bingo. Less dense material. Less dense minerals. Yeah. So they're made up of minerals like more sodium-rich plagioclase, potassium feldspar. They don't have the olivine and they don't have the pyroxene, and so they are more buoyant. They don't want to subduct. And so you can model this glomming on of oceanic islands by putting your hands back where they were, and if you have rings or bracelets or a watch on your left hand, as you move that subduction zone, those things are going to get caught up. And actually, that's exactly what happens. Those islands get squished against the continent in a process that we call accretion. So what that creates are things called accreted terrains. And there's a great example of an accreted terrain just to the west of us in Stanley called the Seven Devils Group. Has anyone ever heard of the Seven Devils Group? So that is an island chain that got squished against North America during the late Cretaceous. And there's a series of those oceanic islands that got accreted terrains, extending all the way to the present-day west coast of Washington, Oregon, and Northern California. So the Wallowa and the Blue Mountains are examples. There's all sorts of names of them that we don't need to know, but those are all accreted terrains, and they all kind of contribute to this crustal architecture of the Northwest. Okay, the most exciting thing that happens during subduction is the formation of volcanoes, and maybe I'm biased, but everyone loves a good volcanic eruption. And contrary to popular belief, the Earth's crust isn't floating on a pool or an ocean of molten material, liquid hot magma. It's really just hot and solid rock that's more akin to silly putty. It kind of behaves as a plastic, but it's not molten. And it's actually really difficult to melt those rocks. Those rocks do not want to melt. They're very happy being hot and solid. And it takes a push to create magma in Earth's mantle. In subduction zones, this push comes from the addition of water, which acts as a natural flux, or something that lowers the melting point of a material. Luckily, water is really easy to come by in a subduction zone because those slabs of oceanic crust have been absorbing water since their formation. And during subduction, that oceanic crust is getting subjected to increasing heat and pressure that causes that water to essentially boil out and migrate into the overlying mantle. Here it lowers the melting point of the mantle, and causes partial melting of that mantle to occur. Now, those pods of magma are much more buoyant than the surrounding solid rock, and they migrate upward until they encounter the crust, and then they begin melting the crust, and then all of those magmas buoyantly rise through cracks in the crust until they coalesce into magma reservoirs. As that subduction zone, as long as that subduction zone is active, you'll have magma reservoirs occurring along that entire stretch of subduction. And those magmas can either cool into a solid rock without ever reaching the surface, or they can feed eruptions of overlying volcanoes, just like is currently taking place with the volcanoes of the Cascade subduction zone, like Mount Lassen, Mount St. Helens, and Mount Rainier. The Idaho Batholith was formed between 4 and 25 kilometers below the surface, and if any volcanoes were associated with these magmas, they've long since eroded. What we're left with are pods of granites and granodiorites, so rocks that contain quartz, sodium-rich plagioclase feldspar, pink potassium feldspar, and then those hornblende biotite micas. And the biotite, or let's see, those individual blobs of magma that coalesce to the Idaho Batholith it's not a big homogeneous feature, and I'll talk about that in a second. So you can see a depiction of subduction. This is caused by the Farallon Plate, which is an oceanic plate precursor to the present-day Juan de Fuca Plate, occurring in the late Cretaceous. I think this is figure 4 of your packet. So what you're looking at is the accretion of oceanic islands, just like the Blue Mountains. Again, the subduction of that oceanic crust, partial melting occurring at that boundary between the mantle, and then that magma upwelling through the mantle, through the crust, where it coalesces to form a batholith, in this case the Idaho Batholith. So as I mentioned, the Idaho Batholith is predominantly granodiorite and granite, and I've mentioned those primary minerals as being quartz, potassium feldspar, plagioclase, biotite mica, and those are the same minerals that make up the continental crust. And however, because this subduction zone was so long-lived, almost 50 million years of activity, and these magmas were in place at different times, the Idaho Batholith is not internally homogeneous. Instead, it's made up of not one, but 2 distinct lobes. The smaller Bitterroot lobe that's in the north, and that was formed between 85 and 65 million years ago, and the much larger Atlanta lobe to the south, which is where we are, and that was formed between 100 to 75 million years ago. Because it likely extends beneath the Snake River Plain, the Atlanta lobe is really the focus of today's presentation. I'm not going to be discussing the Bitterroot lobe. You have to invite me back for that one, I guess. You can see a map showing both the Atlanta and the Bitterroot lobes on page 3, figure 5 of your packet. The different colors represent slightly different mineral contents and ages, but all of these zones are collectively part of that Idaho Batholith. Okay, now let's hop in our time machine, head to 17 million years ago. Around this time, things started getting really exciting on what was otherwise a pretty boring Snake River Plain area. This is when a plume of superheated material from the core mantle boundary passed through the continental lithosphere, eventually reaching the upper layers of the crust right beneath northern Nevada and southern Oregon. And as it melted the overlying crust, it created very large magma reservoirs. And let's do another geology exercise with our hands. I want you to point your left index finger up and then place your right hand on top of it like this. Now slowly move the palm of your right hand over the top of your index finger so that your thumb is kind of pointing to your chest and moving toward you. You've just replicated the motion of the North American plate over the relatively fixed Yellowstone-Snake River Plain hotspot. Most hotspots don't move very much. They don't kind of migrate around like this. They do a little bit of wiggling, but that movement comes from the North America, or whatever plate is overriding the hotspot. Excuse me. So as that tectonic plate moves over the hotspot, magma rising through and melting the overlying crust forms chains of volcanoes that increase away from where that hotspot is currently melting the rock. So an example, a great example of this is the Hawaiian island chain. You can look at a map of Hawaii and see these increasingly larger islands. That also correlates to age, so they're increasingly younger to the Big Island. And that's due to the Pacific Plate. It's slowly moving. The Pacific Plate is slowly moving to the northwest. And a new volcano island is forming to the southeast of the Big Island of Hawaii. And we can actually track the motion of the Pacific Plate by looking at the ages of those islands that make up the Hawaiian chain. So closer to us in Stanley, the Snake River Plain, which many people think is, well, maybe rightly, think it's boring to drive across. For scientists, it's extremely interesting because it is the only example on Earth of a hotspot interacting with the continental crust. We can't see this anywhere else. So next time you're driving through Twin Falls and you're just miserable, think about that. This is very special. It's a special place. And we can see, actually, most of these caldera complexes that make up the Snake River Plain have been covered up by basalt lava. But we can see ash layers on the margins of the Snake River Plain that really give us a lot of information about what was taking place over the last 17 million years. So the oldest caldera complex, actually I'm going to refer you to figure 6. That shows a map showing those caldera complexes with Stanley as a blue dot. So now it's blue. The oldest caldera complex that's depicted in that map is the McDermott. That's on the border between northern Nevada and southern Oregon. That caldera erupted about 16.5 million years ago. Then the Hawaii Humboldt caldera erupted 16 million years ago. And we move to the east, we see the Bruno Jarbidge caldera that erupted between 12.7 and 10.5 million years ago. The Twin Falls caldera erupted between 10.5 and 8.6 million years ago. The Peekaboo caldera, which is my favorite name, erupted between 10.2 and 6.6 million years ago. Heisey erupted between 6.62 and 4.5 million years ago. And finally, the Yellowstone caldera erupted between 2 million years ago and had its latest eruption about 650,000 years ago. And the current location of the hotspot is actually beneath Red Lodge, Montana. So if you're looking at real estate over there, maybe make other choices. Stay in Stanley. Okay, so the map that's depicted is a little bit simple, especially where those easternmost calderas are concerned. Because instead of it being one big supervolcano, one big eruptive center, there's actually a bunch of nested caldera complexes in the Peekaboo and the Heisey and the Yellowstone volcanic centers. And that's going to be important later on when we talk about how the characteristics of these supervolcanoes change geographically. For example, the Peekaboo caldera complex had up to 17 individual massive eruptions that would have created, nasty piles of ash and large-scale destruction. So these were happening pretty frequently from the same magma chambers. Excuse me. Because the hotspot, so let's talk about why those eruptions are so nasty. Because the hotspot is melting continental crust, we're melting minerals like quartz, sodium-rich plagioclase feldspar, potassium feldspar. All of those minerals have a lot of silica in them, so they actually produce very sticky, viscous magmas that don't allow gases to escape. And that's in contrast to when we melt the oceanic crust, which is what's taking place in Hawaii right now. Those magmas don't have a lot of silica because they're not melting minerals like quartz and those typical continental crust assemblages. So in Hawaiian eruptions, that magma is really gentle when it erupts, and it typically flows really well, which is the opposite of what we see in Yellowstone. So this is what leads to supervolcano eruptions. When we melt the continental crust, we get these really sticky magmas, and they produce a lot of ash. So let's talk more about supervolcanoes. They're huge. They involve enormous reservoirs of magma. We can actually see these depicted in seismic tomography, so we can shoot energy into the crust and actually see these areas of massive hot zones within a much cooler crust. So very thick, very viscous magma that involves cyclical eruptions. So it's not typically one big eruption. This magma chamber is erupting and then refilling over time. And as these eruptions progress, those magma chambers will empty. All of that ash is coming out and it's removing volume from the magma chamber. And that causes the roof of the magma chamber to collapse downward. So it's kind of like a sinkhole in Florida. When you pump out groundwater, that overlying material sinks down, it subsides. But this is much more violent. It creates huge amounts of ash. And if this sounds familiar, that's good. Not just sinkholes in Florida, but also this is the very mechanism that formed the Yellowstone caldera 640,000 years ago during the eruption of the lava creek tuff. And it's important to note that caldera-forming eruptions are many orders of magnitude larger than the eruptions that we've observed over the last 500 years. For example, Yellowstone's last eruption was 4,000 times larger than the eruption of Mount St. Helens in 1980, and 200 times larger than the eruption of Mount Pinatubo in 1991. And that's just one of the eruptions from Yellowstone. There was 2 others. So these are enormous and exciting because they're, you know, it's like disaster. It's exciting, you know, I don't know. So although each of these eruptions was catastrophic in its own way, the supervolcanoes that erupted along the Yellowstone-Snake River Plain vary greatly from one another. So we do see a lot of characteristics that shift as we move from the McDermott caldera to the west to the Yellowstone caldera to the east. Some of these caldera complexes were active for several million years and created several small eruptions. Those are examples of those would be the Peekaboo caldera complex, the Heisey caldera complex, and Yellowstone, while others created 1 or 2 mega eruptions over a much shorter period of time. And examples of those would be the McDermott and the Owyhee-Humboldt caldera complexes. Some supervolcano eruptions were extremely hot and voluminous. Examples of those would be the Bruno Jarbidge and Twin Falls eruptions. But collectively, all of these eruptions along the Yellowstone-Snake River Plain hotspot track are exciting because they not only obliterated the landscape, removed all of the vegetation and animals, leading to widespread ecologic collapse, but they also carry with them fascinating geologic information that can tell us a lot about what's going on in the crust and what's going on with the plumbing systems that feed magma to the surface. And most of that information comes from those very tiny minerals that are carried in volcanic ash. And those minerals are zircons, and yes, they're the same minerals that we talked about earlier. So now I'll provide a bit of information about why zircon is such a powerful tool in understanding supervolcanoes along the hotspot track, as well as the rocks of the Idaho Batholith, and then how we can use that information to link the continental crust of the northwest U.S. to eruption characteristics of those supervolcanoes. If you recall, zircon is both very common in rocks in the continental crust, but also extremely durable, meaning it takes a lot of heat and pressure to melt those minerals and destroy the information that they carry. This means that any information that's stored in the zircon as it crystallizes is preserved and accessible to us. So now I'm going to do a little bit of isotope geochemistry for you. This is going to be not like college chemistry. We're going to just dip our toes in, just familiarize ourselves enough so that we can move forward. But zircons carry with them naturally large amounts of uranium and hafnium. Hafnium is a lesser known isotope that's very easily incorporated into that zircon crystal lattice as the zircon is forming. Both of these elements have isotopes, and they both undergo radioactive decay over time. Now, isotopes, if you don't remember your chemistry class, are just varieties of elements that have the same number of protons and electrons, but different numbers of neutrons. So they can be either heavier or lighter than they should be. Oftentimes the heavier ones are more unstable and typically more likely to undergo radioactive decay. We call the original element, the starting element, the parent isotope, and then the element that it decays into over time, over a set period of time, is the daughter isotope. And we can use the half-life of the parent isotope, or the time that it takes for half of that parent isotope to decay into the daughter isotope, to calculate the age at which that mineral formed, which that rock formed in a magma. You can see a cartoon illustrating radioactive decay from parent to daughter isotope and see how half-lives are calculated on page 5. And a good summary of this is that the older the mineral, the more daughter isotopes will be present. The more of those parent isotopes will have decayed into the daughter isotopes. The younger the rock is, the higher that parent to daughter isotope will be, because you'll have more of those parent-daughter isotopes. And it's really great because this graph that's showing the decay series with half-life on the x-axis and percent of parent isotopes shows zircons. So this should look like a similar outline as that page 1 in your figure packet. We saw the zones of the zircon because this is one of our primary tools for understanding radioactive decay in minerals is actually a zircon. So if you were wondering, if you thought I was just making up numbers when I was telling you the ages of the Atlanta and the bitter lobes, I wasn't. This is all information that we've collected from zircons. Lots of zircons that have been collected from outcrops of the Idaho Batholith and analyzed using special instruments. When minerals like zircons crystallize in a cooling magma, the elements that are in that crystal lattice get stuck there and they can't escape. Therefore, radioactive elements like uranium and hafnium will decay into their daughter isotopes without any information escaping, without any daughter isotopes leaving that crystal. So we can use very special and very expensive instruments to count the number of parent versus daughter isotopes, and that gives us an age for that zircon and the rock that it crystallized in. Because it has a relatively short half-life, and because it's very common in the zircon, as well as the fact that it has multiple parent-daughter isotope pairs that we can use, uranium is an excellent dating tool for zircon. On the other hand, hafnium is not as useful because it has an extremely long half-life and therefore isn't useful at all for dating zircons. However, hafnium does tell us the origin of the magma that crystallized into the rock. Magmas that form from the melting of Earth's mantle have very specific and unique hafnium values compared to magmas that form from the melting of continental crust. And even within the continental crust, we can identify magmas that form from the melting of different rock types, like a magma that formed from the melting of a sedimentary rock or a magma that formed from the melting of a metamorphic rock, just by looking at the hafnium signature. So you can think of it this way. Uranium and zircon gives us important information about the timing of formation, making zircons like a rock stopwatch. And hafnium in zircons makes it a really useful fingerprint for determining where that magma came from. Because they crystallized under the same conditions within the same time frame, zircons and the Idaho Batholith have very similar uranium and hafnium values. So we can look at a rock sample and identify the Idaho Batholith just by looking at those zircons. Uranium and hafnium values in zircon tell us that the Idaho Batholith incrementally formed between 65 and 100 million years ago as the result of subduction. So we can see that subduction signature in the hafnium, and we can see that age signature in the uranium. As an aside, zircons from the Idaho Batholith are also helpful for understanding the evolution of river systems in Idaho. So rivers that cut through and erode the Idaho Batholith carry with them zircons and sediment that allow us to track the location and extent of rivers like the Main Salmon. Okay, now that I've explained the importance of zircon as a rock stopwatch and a fingerprint, let's return to those supervolcanoes. When hotspots interact with the continental crust, they essentially act as a blowtorch and just obliterate and melt everything above them, creating the magmas that feed supervolcano eruptions. But since zircons are incredibly resilient, they aren't melted, and they're often preserved in these magmas as inherited zircons. Eventually, during supervolcano eruptions, those inherited zircons are erupted along with very young zircons that crystallized within that newly formed hotspot magma. And so when eruptions occur, that volcanic eruption, or that volcanic ash, carries with it the inherited zircons that are really old and have a distinct hafnium signature, as well as extremely young zircons that are produced by that brand new magma. So we'll use an example. If a magma forms in the Idaho Batholith inherited zircons from the Idaho Batholith will be integrated into that magma reservoir along with brand new zircons that crystallize from the magma. So we'll see aged populations of between 65 and 100 million years ago, and then we'll see brand new 1 million year old zircons or whatever age of that eruption, all within the same volcanic ash deposit. Plus those zircons will have very different hafnium values that can give us a sense for how or what sort of geologic process led to their formation. So we're going to skip ahead in your figure packet. The last page. This is a little cartoon that shows the integration of inherited zircons and brand new baby zircons formed from a hotspot. So this figure is a little bit complicated, but what we're seeing at the bottom of the page in that box labeled upper mantle is the hotspot, the Yellowstone-Snake River Plain hotspot, reaching the lower crust of the North American plate as it migrates over it at a rate of about 2.3 or 2.4 centimeters per year, which is a bit slower than your fingernails grow. In the lower crust, if we move up a box, that heavier basaltic magma is creating a sill complex. Basalt magma, just like the oceanic crust, is really dense. It's made of those dense minerals like olivine and pyroxene, and so it kind of stagnates, but it's still extremely hot, so it's melting the surrounding material, and then magmas are migrating up into the continental crust, that uppermost box, where they melt the surrounding rock, which could be Idaho Batholith. As they do, they integrate those melted, that melted material, which can include inherited zircons, and then all of that material can get erupted as volcanic ash. So the ash deposits that we've sampled on the Snake River Plain can contain a collection of inherited zircons, which are typically much older, and then those brand new baby zircons that are formed from that hotspot magma. Again, both types of those zircons have distinct uranium and hafnium values. Okay, so we know that zircons recovered from ash erupted during supervolcano eruptions on the Snake River Plain can tell us what types of rocks were melted by the hotspot. And we also know that the eruption characteristics of the Snake River Plain supervolcanoes change from west to east, going from massive higher temperature volcanic eruptions to much smaller, lower temperature, but more frequent and more numerous eruptions to the east, to the present day location of Yellowstone. Zircons recovered from each of these calderas have unique uranium and hafnium values that tell us their age and magma source, and surprise, there are a lot of differences. So to illustrate this concept, I'm now going to refer you to figure 9 on page 6. And this is the last graph I'm going to show you, and I'm going to walk you through it because it's pretty complicated. First, let's look at the y-axis. This is epsilon hafnium, which is a value calculated using that ratio of parent to daughter isotopes. Positive values indicate that the rock was sourced from the melting of igneous rocks from Earth's mantle. So you can think of this as being, if we melt the oceanic crust, we're going to get positive values. If we melt continental crust, we get negative values. And if we melt really old continental crust, we get extremely negative values. So that's one clue for determining our geologic source. Now let's go to the x-axis. This shows millions of years. This is calculated from those uranium isotopes that decay to different daughter isotopes. We're using half-life to calculate an age. If we look at the left side of the graph, so moving all the way kind of toward the origin of the graph, we can see zircon ages and hafnium values from eruptions from the oldest Snake River Plain, Yellowstone supervolcano eruptions, McDermott and Owyhee Humboldt. And those again erupted between 17 and about 13, actually 16.5 and 16 million years ago. And feel free to refer back to your map on page 4 for a visual reminder of where these supervolcanoes are located. But I'll continue to give kind of general geographic information about where each of these are. So hafnium values from those two volcanic eruptions, the furthest west, are between 5 and 40. They're a bit scattered, but most fall into that 5 to negative 40 range. When we move eastward to eruptions between 13 and 9 million years ago, the ages of the Bruno Jarbidge and Twin Falls caldera complexes, we see see a range of hafnium values, most of which are between -5 and -10, but some of which are as low as -27 or as high as 13. Then, between 9 and 5 million years ago, the eruptions of the Peekaboo and Heisey caldera complexes give us our widest scatter of hafnium values yet, between -37 and -3. Our youngest zircons are from those eruptions of the Yellowstone caldera complex. Those are between 2 million years and 640,000 years old, and those have ranges between 25 and -2. But most of those are between about -2 and -13. So what do all these numbers tell us? As I mentioned earlier, those higher positive values indicate magmas that are more similar to Earth's mantle, while negative values indicate magmas that are formed from the melting of continental crust. More negative means much older, less negative mean younger. So if we have a very negative value, that might indicate a metamorphic rock like a gneiss, and those less negative values could be younger igneous intrusion like maybe the Idaho Batholith. So if you turn to figure 10 of your packet on page 7, you can see a map showing the rocks that make up the continent, the Northwest, with the caldera complexes of the Yellowstone-Snake River Plain overlaid on top. And so now here we are at the crustal architecture portion of this presentation. Remember when I had you all hold up your left index finger and then move your right hand over it? Now imagine, if you want to do this again, you can, along with me. Imagine that your right hand is made up of a bunch of different rocks. And as your right hand is moving over the hotspot blowtorch, you're melting different rock types. And that gives us very different magma characteristics and certainly very different zircon chemical signatures. Each rock produces a different magma composition, which directly influences how those volcanic eruptions will occur. A great example is Hawaii. So we talked about this earlier. The hotspot that's currently forming in the Hawaiian Islands is melting through oceanic crust. So it creates magmas that are more runny and can allow gases to escape much easier. And this leads to gentle volcanic eruptions where we see these rivers of lava. Those you wouldn't mind standing next to, but that's in contrast to our Yellowstone volcanic eruptions, where here in Stanley we probably wouldn't live very long if one of these was erupting, because they're just so violent, and that's largely because of the magma composition not allowing that gas to escape and producing explosive voluminous eruptions. We can't see this crustal architecture, so that map that you're seeing, most of this is covered up by younger rocks, younger sedimentary rocks and igneous rocks in the case of the Snake River Plain, but we do see outcrops here and there. Actually, as my friend and I were driving up here from Logan, I was like, oh, there's the Grouse Creek. You can see the Grouse Creek Mountains over by Twin Falls. And so we do see little patches of these, which allow us to have an understanding of their chemical signatures via zircons. So let's go back to that map on page 7, starting with the westernmost side. In portions of Washington, Oregon, California, and Nevada, we can see the extent of the accreted terrains. Now remember, these are these islands that are sitting on top of oceanic crust that, because they're made of less dense material, instead of subducting, they accrete or glom on to the continent. And these ocean islands have kind of an intermediate composition between the oceanic crust and the continental crust. So they produce very different chemistries, very different magmas when they're melted. These rocks have a hafnium signature that's a mixture between Earth's mantle, which is that positive hafnium value, and the continental crust, which is that very negative value. Eruptions of the McDermott and Owyhee Humboldt caldera were relatively short-lived and small compared to their eastern neighbors, most likely because this magma composition was different, and that's a result of the melting through rocks of the accreted terrains. Skipping a bit east, so we're hopping over to the Peekaboo and Heisey caldera complexes, we see the influence of the Farmington Zone, which is kind of a mysterious area between the Grouse Creek Block and the Wyoming Craton. That's this heterogeneous mixture of metamorphosed sedimentary rocks and igneous rocks, as well as younger igneous intrusions, all from different sources. The hafnium signature for zircons erupted from these caldera complexes has a really wide range, and these eruptions were both smaller and more frequent than supervolcanoes to the west and east, indicating that magmas generated from this melting Farmington zone may have influenced the eruptive style. Further east, the Yellowstone caldera complex sits right above the Wyoming Craton, which is a piece of the ancestral North American continent, so extremely old. And these rocks are mostly made up of metamorphosed granites, or gneiss. And the homogeneous nature of this rock means that the Yellowstone hafnium values are all crustal and all define a narrower range than the Heisei and Peekaboo volcanic zircons. So now we finally get to the part about the Idaho Batholith, influencing eruptive characteristics of these supervolcanoes. And using our crustal architecture map, we can see that the Idaho Batholith and the Grouse Creek Block partially extend beneath the Snake River Plain, near the Bruno Jarbidge and Twin Falls calderas. The Grouse Creek Block is similar to the Wyoming Craton in that it's very old and mostly made up of gneiss, that metamorphosed granite, so it tends to have much more negative epsilon hafnium values, very distinctly negative, like -40 to -30 hafnium. And the Idaho Batholith, in contrast, is much younger, and it's made of igneous rocks from 100 million to 65 million years ago, so it's much more positive. It's still in that negative range, but it's a little bit higher up toward the -10, -15. As far as supervolcano eruptions go, unlike their neighbors to the east and west, both of these caldera complexes, Peekaboo or Bruno Jarbidge and Twin Falls, had enormous, extremely hot volcanic eruptions that created massive rhyolite flows that actually moved. They create folds. You can actually see these if you drive south of Twin Falls today. There are these thick layers that just kind of oozed down slope as they erupted. So erupted at temperatures of about 2,000 degrees, which is extremely hot for this style of eruption. It's about the same temperature, this is a tangent, it's about the same temperature as a basalt lava flow in Hawaii, so extremely anomalously hot. We can see proof of the influence of the Idaho Batholith in the age and the hafnium signature of those inherited zircons that we find in ash deposits from the Bruno Jarbidge and Twin Falls supervolcanoes. Therefore, it's possible that the composition and the extent of the Idaho Batholith has contributed to the behavior of these massive eruptions, and we should all have a lot more respect for the Idaho Batholith now. Okay, and with that, I'm done. I'm happy to take any questions. Yeah, back there.
Is there a relationship between obsidian and zircons?
Oh,
We get told that obsidian is a fingerprint of the volcano.
that's a great question. So the question was, is there, are you saying it, like if obsidian and zircon are similar tools? Is that a good paraphrase? All right. Well, obsidian, this is me putting on my geology teacher hat, is not actually a mineral. It's a glass, so it cools so fast that those elements that are in the melt don't have time to form crystal, they don't have time to form bonds. So it's not as easy to pull out age information from obsidian. We can see chemical information that can tell us the composition of the magma, but as far as being able to pinpoint an age, that uranium that might be in the obsidian is going to get blasted out as it decays. So it's a good geochemical fingerprint, but not so good for determining age. So I would say like halfway there. Great question. Oh, we got a competition. You guys want to rock, paper, scissors? Okay.
So the Snake River Plain, the massive lava flows, are those connected with supervolcanoes or not?
Yes, that's a great question. So there's a bunch of basalt on the Snake River Plain. This was another thing I was annoying my friend Maria about today during our drive. Shield volcanoes all over the place. If you see a radio tower on the Snake River Plain, it's probably a shield volcano, like Kilauea or a Mauna Loa, but much smaller. So after that hotspot, or after the North American plate moved over the hotspot, it still had a lot of residual heat flow. So the hotspot, if it's directly under the continental crust, is going to produce a supervolcano eruption that's had a lot of rhyolite, a lot of ash. But in the aftermath of that, over here, I guess if the hotspot's right there, there's still enough heat flow that it's allowing those magmas to rise to the surface and erupt where we have these low shield volcanoes and really thick lava flows that have built up over time. That's actually more my science, so that's what I typically study, is the volcanic stratigraphy of those basalt flows. So if you want to talk about that, I could talk your ear off. All right, there was another question back there.
So you talked about how the west had really intense flows, and then the east is a little more subdued.
Yeah, and I guess it's all, so the question is, we have this transition from west to east in like the size of eruptions and the volume of material coming out. I should have mentioned this at the beginning. They're all big, they're all devastating, but we just see different characteristics as we move from the west to the east. So kind of more short-lived volcanic eruptions in McDermott and Hawaii Humboldt. Those, you know, there was one at 16 million or 16.5 and then one at 16, and then as we move to the east we have a much wider interval during which those eruptions took place. So it's a timing thing, it's the size of the eruption, it's the temperature, it's all these things together. That was a great question. Yeah?
Maybe to build on that a little bit more, is there something about the composition of the rocks for the Bruno Jarvis Twin Falls, so in other words those influenced by the Idaho Batholith, that have caused these more massive eruptions?
Yeah.
Or have you even gotten to that point in your research? I don't know.
That's a great question. So is there something about the Grouse Creek Block and the Idaho Batholith? You know, that's a great question. The Grouse Creek Block is really similar to the Wyoming Craton, so we would almost expect supervolcano eruptions, those ash flows, to be very similar in all of their characteristics to the Yellowstone eruptions, which took place over that Wyoming Craton. So it's possible that something in the Idaho Batholith, because it's a subduction zone origin, because it's a result from the mantle melting, partially melting due to that subducting plate, that there's some signature that's creating that those explosive conditions. But there's a lot we don't know. This is, as we would say in geology, you know, a solid line denotes a lot of confidence in our contact and in our interpretation. This is very dashed line. This is a lot of arm waving, but it's a good point. Yeah, back there.
Is there any correlation between the emplacement of the Idaho Batholith and the Chalice volcano?
Ooh, great question. Is there a correlation between the emplacement of the Idaho Batholith and the Chalice volcanic field? Yes, they are both related to that subduction of the Farallon plate. And actually, volcanism or magmatism kind of migrated to the east as that Farallon plate was subducting, because it started out with this kind of geometry, and then it kind of shallowed, so it became that angle of subduction decreased. And so magmatism migrated eastward along with it. And so the Chalice volcanic field is slightly younger. It's Eocene, so about 45 million years ago, or 45 million years old, whereas the Idaho Batholith is that late Cretaceous time. So yeah, same mechanism, both related to subduction. Any other questions? Yeah.
So I'm curious, with the Farmington zone, which is like the mashup of a bunch of different stuff, it says in here that it's unknown origin. Are there any hypotheses for that? 'Cause that's like the northern part of the Wasatch, right?
Yeah, it's actually a lot of the Wasatch between, like, you know, I don't know if you've driven that,
I used to live in
that
Salt Lake,
hellscape
so,
of
yeah.
I-15.
Yeah.
Yeah, there's like a little bit of a bump out, and then everything from basically Bountiful up to Ogden, actually to Brigham City, is Farmington Canyon Complex, and there's so many different rock types. There's amphiolites, there's quartzites. It's thought that it could be a suture, so a place where two land masses crash together. It's thought that it could be a subduction zone. Everyone has their idea, and there's a lot of little geology controversy, people getting fiery about their ideas. So I tend to stay away. I'm just like, it's mysterious, we don't know, because I don't want to dive into that. Any other questions? Yeah.
This is sort of out of left field. Are you familiar with the ashfall fossil beds?
Yes, those are really cool.
Okay, it says that from one of these eruptions?
Ah, I have to think about that. Are you talking about like John Day? or?
No, this is in
Oh, Glenn's Berry?
Nebraska.
Oh, sorry.
So there's a massive eruption that buried a whole bunch of rhinos about 10 million years ago from somewhere far in the west. I just wondered if it was one of these.
Oh, it could be the Twin Falls. Could be Twin Falls caldera. I mean, I didn't put this in the packet. I was getting a little carried away, and I was like, I'm gonna make them mad because they're printing out so many pages. But if you can look at the airfall extent of the Yellowstone eruptions, and it does extend all the way out into Nebraska. So if we think about prevailing wind directions and the volumes of these, it's very likely that something like a Twin Falls eruption could have caused that devastating situation for those creatures. This is what I tell my students, is it's better to get wiped out immediately than to just be around and starving to death and eating your pets, and this is bad. So it's dark times. We don't want to think about that. All right, I think that there aren't any other questions. Thank you all so much. This was really fun.